The absorption of visible light can induce significant changes in the electronic structure of molecules, playing a crucial role in various photoactivated processes. While most photoexcited states have extremely short lifetimes, certain systems can be trapped in a metastable state for extended periods, enabling photoswitching between distinct physical and chemical properties. This phenomenon has led to the development of photoswitchable materials with a wide range of applications, including light-responsive molecular junctions, molecular valves and machines, information storage and processing devices, and solar energy harvesting. One well-known example is the photoisomerization of rhodopsin, the protein responsible for vision in humans and many animals. In the field of photoswitchable materials, research efforts have primarily focused on the light-induced isomerization of organic molecules, with some attention given to inorganic compounds such as transition metal nitrosyl complexes. However, organic photoswitches do not exhibit changes in magnetic properties upon light absorption, which has limited their applications. To achieve photomagnetic responses, organic photoswitches must be coupled with metal centers, but this approach has only produced paramagnetic systems so far. In contrast, inorganic photomagnetic compounds typically rely on spin crossover, SCO, sites, which display light-induced excited spin state trapping, LIEST, originating at the metal center. The practical applications of most SCO systems as photomagnetic switches at room temperature are limited due to rapid thermal relaxation above 80 K. However, a careful analysis of the microscopic origins of their photomagnetism offers insights for designing high-temperature magnetic photoswitches. For instance, in the Fe2LN5CN MAOH SCO complex, the formation and breaking of a coordination bond extend the lifetimes of its photoexcited state, which can be observed up to 130 K. Building on these insights, researchers have proposed a strategy towards high-temperature photomagnetic systems based on photochemistry, specifically the photodissociation of cyanometalates. In this study, we demonstrate a fully reversible metal-cyanide photodissociation occurring in single crystals of potassium heptacyanomolybdate dihydrate, K4MO3CN 2H2O 1. The single crystals of 1 undergo a complete metal-cyanide bond photodissociation upon absorption of violet light, resulting in the formation of a hexacoordinate complex, K4MO3CN6 2H2O. Remarkably, compound 1 is fully recovered through red light absorption of 2, representing a solid-state ligand photoassociation reaction. These transformations are non-destructive and maintain the crystallinity of 1 throughout the process. The photochemical switching behavior of 1 was thoroughly characterized using a combination of techniques, including single crystal X-ray diffraction, SCXRD, infrared IR and electron paramagnetic resonance, EPR spectroscopies, optical reflectivity studies, and X-ray absorption spectroscopy, XAS, complemented by magnetization measurements and X-ray magnetic circular dichroism, XMCD. The results revealed that the photodissociation of Mo3 iron 7 4- leads to the formation of Mo3 iron 6 3- and a free Cn- anion trapped between H2O molecules and K+ cations. The reversible photodissociation of the metal-cyanide bond was confirmed by IR spectroscopy in a polycrystalline sample of 1. XAS measurements at 4K before and after irradiation supported the photo-induced formation of Mo3 iron 6 3-. The magnetic and in situ photomagnetic studies of 1 were conducted using variable temperature/magnetic field magnetometry with light delivered to the sample chamber through an optical fiber. The temperature dependence of the KT product measured at 0.1 T for pristine 1 showed behavior typical of an S equals half, G equals 2.0 paramagnetic system, in agreement with the EPR results. Upon cooling below 50 K, The KTT data deviated from the constant value of 0.36 centimeters cubed -K-mol, ultimately decreasing to 0.03 centimeters cubed -K-mol at 1.8 K, indicating supramolecular antiferromagnetic interactions between S equals half Mo3 spins. Below 3.5 K, these couplings led to an antiferromagnetically ordered state, as evidenced by the MH data, and corroborated by low-temperature heat capacity measurements. Photomagnetic experiments conducted on 1 at 10 K showed an increase in KT from 0.30 to 1.79 centimeters cubed -mol upon 405 nanometer irradiation, converting 1 into 2. The KTT profile, recorded in the dark immediately after irradiation, revealed a plateau around 1.84 centimeters cubed -K-mol in the 20 to 100 K range, close to 1.875 centimeters cubed -group mol expected for a magnetically isotropic S equals 3/2 state. Additionally, the MH dependence for 2 showed a magnetization close to 3.0 particles at 7T, indicating a high-spin S equals 3/2 configuration, in good agreement with XMCD results and the magnetic data for 3. Collectively, these photomagnetic experiments at 10 K suggest thermal trapping of the S equals 3/2 metastable state, analogous to spin crossover systems, confirming the formation of a light-induced high-spin heptacyanomolybdate 3 complex. As the temperature rises, the photo-induced state relaxes to the original S equals half ground state of the Mo3 CN7-4S complex around 150 K, indicated by a sharp drop in the Chi-T product. Notably, the relaxation temperature of 150 K for 2 surpasses that of previously reported spin crossover systems, suggesting an unusually long lifetime of the photo-induced state in this molybdenum-cyanide complex. To quantify the characteristic time of the thermally induced 2-to-1 relaxation, time-dependent magnetization studies were performed at several temperatures in the 132.5 to 147.5 kilogram range. The temperature dependence of the estimated relaxation time followed an Arrhenius behavior with an activation energy of 4,770-90 kilograms. Hence, with increasing temperature, high-energy states become populated, enabling 2 to overcome the energy barrier of cyanide reassociation and relaxation to 1. The relaxation behavior of 2 is comparable with that reported for the record-holding photomagnetic molecular Prussian blue analog, Co4 Fe460. Importantly, the substantial energy barrier of the thermally activated metal-cyanide association 2-to-1 does not prevent this process from happening under 638 nm irradiation at low temperatures, as demonstrated by SCXRD at 30 K or optical reflectivity at 10 K. Photomagnetic experiments at 10 K further supported this observation, following the initial 405 nm irradiation of 1 at 10 K, which photoconverts 1 into 2. A subsequent 638 nm irradiation fully restored the magnetic susceptibility of 1. In summary, a single crystal of the inorganic compound K4MoIICN7.H2O demonstrates a reversible photochemical reaction, enabling the molybdenum center to switch between the 7-coordinate low-spin and 6-coordinate high-spin geometries. This bidirectional photoswitching is remarkably robust and non-destructive, yielding colossal structural, electronic, and magnetic changes. Interestingly, photodissociation in solution is irreversible, permitting isolation of the UHO Mo3 C2H. K4 Mo3 C2 2H2O stands out as a unique example of bidirectional photoswitching in an inorganic coordination compound in the crystalline phase, contrasting with the previously reported K4 Movar C2H 2H2O, where cyanide reassociation proceeds exclusively through the thermal route. The high performance of K4MO3 Pho is highlighted by three key factors. 1. Photo-induced ligand dissociation achieves 100% efficiency. 2. The photodissociation is fully reversible with light of a different wavelength, resulting in photoassociation. And 3. The record-high relaxation temperature allows photoswitching at temperatures exceeding 100 K. These exceptional photochemical properties set the stage for designing new photomagnetic materials that could switch between paramagnetic and ferromagnetic or ferrimagnetic states at room temperature.